Hello and welcome to my final video presentation for Mechatronics 2 in Reykjavik University. To recap from the midterm, my project is to stabilize a levitating magnet using a PID control loop while getting positional input from the magnet through Hall effect sensors and then subsequently actuating the magnet by using electromagnets. This project consists of three major systems, those being the electrical, the software and the hardware systems. Once completed, the desired capabilities will be to be able to stay within 1% error of the steady state, reach stability without oscillations within around 5 seconds, and to be able to support loads in the range of 0 to 0.2 kilograms. The electrical systems requirements were broken down into this block diagram with each block representing an individual electrical system. The amplifier system was quite possibly the most complex electrical system in this project. This is due to the fact that the signal is very small and is offset by a relatively large amount, so the signal cannot simply be amplified by a large amount without hitting saturation. The chosen circuit to solve this issue is to use a differential amplifier that amplifies the difference between the signal and a biasing voltage created using a second op-amp acting as a unity gain amplifier to produce a voltage source with practically no series resistance. The circuit worked great in simulation. However, when the circuit was built on a PCB, it did not work and the voltage follower was giving erroneous values. This turned out to be due to the fact that I was using the LM741 op-amp, which has a minimum supply voltage of plus minus 10 volts, but the circuit works on a 5 volt logic level. The solution to this was to purchase a new op-amp that is better suited for the task. The selection of op-amps was limited by the stock at eHlutir.is as shipping was delayed from online retailers due to the COVID-19 pandemic. As the circuit had already been designed for the LM741, one criteria was that the purchased op-amp would have the same pinout as the LM741, thus being able to utilize the existing circuit and that the op-amp worked at the desired voltages. These criteria gave this table of options, and finally the CA3140 was selected, and this works beautifully. The electromagnets and electromagnet driver have not changed since the midterm evaluation. These components work sufficiently for this project. However, the electromagnets have some issues that will be described later in this video. Once all electrical subsystems had been tested or simulated, I designed a full system schematic that can be seen here. From the schematic in the last slide, the PCB here on the left was designed and cut on the Bantam mill at Reykjavik University. The PCB on the right was then quickly designed and milled in order to hold the Hall effect sensor and connect them to jumper wires that lead to the main PCB. Since the circuit schematic is relatively complex, I had initially planned on ordering the PCB from China. However, this was not possible due to the current situation of the world, so I used the mill at Reykjavik University and had to do a few test circuits in order to fine-tune the use of the mill and soldering SMD components on a milled PCB, as can be seen here. The software diagram for this project has remained much the same from the midterm. Since then, all necessary libraries have been implemented in C code. The mechanical design of the project has developed somewhat and has required a few revisions since the midterm. However, the basics are still the same, namely that the base simply holds the 4 electromagnets and 8 neodymium magnets around the base. The base has however been modified to hold the PCB with the Hall effect sensors, and the biasing magnet that will be explained in later slides has been added. As with all projects, the development road was not perfectly smooth, and a few issues were found and subsequently solved along the way. The three main problems are those described here, namely that the magnets around the base induced a magnetic field in the ferric core of the electromagnets, and that the sensors reached saturation from the magnetic field from the magnets around the base, which meant that the levitating magnet gave no signal. The third problem, that being the COVID-19 pandemic, couldn't exactly be solved by me, as I am not a specialist in virology, but the effects of it on my project were largely mitigated by learning to use new tools, as I no longer had access to the lab at Reykjavik University. The effects of this did, though, have an effect on how quickly I could make progress and find the source of problems. As mentioned, this problem was caused by an induced dipole in the ferric core of the electromagnets due to the base magnets. The effects of this was that it accentuated the saturation of the Hall effect sensors, and that it caused an inflection point in magnetic field above the base, causing a point that below which the magnetic field, instead of repelling the levitating magnet as is desired, would instead attract it, making the system less stable. This, in future, will be solved by purchasing new electromagnets that lack this ferric core, thus mitigating this problem. This problem happened to be rather tricky, due to the fact that I was already sensing a small signal, and I suspected that the lack of signal was caused by the sensor not being able to sense, or not being sensitive enough, and not that the sensor had in fact reached saturation and could not sense a greater magnetic field. Once the source of this issue had been found, two solutions came to mind. The first of which was simply to order new sensors that were rated for a greater range and could thus sense in the desired range. This did not work, as the sensors that I ordered would still reach saturation. The second solution that came to mind was, instead of fixing the sensors, I would fix the system and try to bias the magnetic field within the range using a smaller magnet beneath the PCB. This solution worked, and the selected distance from the PCB was determined through experimentation so as to not bias the field too far in the opposite direction, saturating it again. Every issue hit and solution found has been documented in this notebook that has been digitized. So if you wish to learn more about the specific problem solving steps taken, you can view the PDF file at the given link. This project is still ongoing, and I will continue working on it in the following months. As this is the case, the system cannot yet stably balance a magnet. However, for the scope of this project, the control board, software libraries and mechanics have all been successfully designed and tested and appear to work. The remaining part of this project will be to properly simulate and tune the PID control system in order to reach stability within the specified margins. I had hoped to complete this task during this term, but due to the problems that took longer to solve than I had expected, I ended up not having time to do so. However, I have completed everything that connects to the microcontroller, and most importantly, I've learnt a great deal with regards to working with a microcontroller and with PCB and software design. Here you can see the estimated and real time spent on every component of this project. These values aren't entirely accurate, as often I'd work on two elements simultaneously, but log the time spent on both tasks in only one category. But the total time is close to being accurate. Thank you for watching this presentation. If you have any questions, please email them to oscarp17@ru.is. Thank you.